Good evening, ladies and gentlemen. Welcome to another USOMI webinar. It's with pleasure that I'd like to introduce you all to Jonas Teuwen, who joins us from the Radboud University Medical Center and the Netherlands Cancer Institute. He's a scientist by background with a PhD in mathematics and is now a group leader in AI research and its application to oncology. I'd just like to thank Barco for sponsoring this session today. And I'm your host, Dr. Shah Islam, with Daniel Pinto dos Santos, and we'll be co-chairing this session. So without further ado, I'd like to hand it over to Jonas to start this very topical lecture on accelerated MRI with AI.
Thank you for the introduction, and indeed I will talk about accelerating MRI with AI. And you might have seen in the media there has been quite some fuss about the Facebook paper where they show that you can accelerate knee MRIs by a factor of 4 and still get good diagnostic performance. So for a brief overview of my talk, I first like to convince you why you would actually want to accelerate MRI with AI. So I'll touch upon that it opens opportunities for new applications, and it allows you allows to build end-to-end deep learning models. I'll also show you there are several ways to accelerate MRI with AI. I'll show you my solution, of the solution of my team, which are recurrent inference machines. I'll touch upon the MRI reconstruction challenges where we use this model. And we got the top spots in 2 of them. And finally, also mention something about open source software we developed to be able to do MRI reconstruction with AI. So this is something which is, of course, well known to you, but magnetic resonance imaging has an important role in medicine. And this is also witnessed as by the fact that the 2003 Nobel Prize in Medicine was given to the scientists that designed the hardware and the acquisition method that allowed the imaging of human tissue with magnetic fields. And one of the key ideas they had was that the measurements, that the relationship between the measurements in the machine, the so-called K-space, and the image itself is given by the inverse Fourier transform. So this is something which is very easy to compute, and allowing to quickly iterate between different types of acquisitions. So here in the image, I do show you just a real valued image, but in practice, these are complex valued images, and we don't only get the magnitude image as you see on the right, but also the phase data. But in essence, the Fourier transform maps from complex K-space to the image, which is also a complex image. So I try to argue why we need it. So one important limitation of MRI is that it's rather slow. So a typical MRI exam with all the different acquisitions can still take up to 45 minutes, and this hasn't changed much in the past decades. And an obvious disadvantage of this is that it becomes expensive because the scanner is occupied, and we can scan less patients in each day. And there's also limits application areas. So this is one possibility of image-guided biopsy. So on the image to the left, there is a prostate needle biopsy where we want to visualize on which part of the prostate the biopsy is acquired. So this right now, as you see, this is for each different needle position, a new acquisition is made and this image is reconstructed. So if we could do this in a real-time fashion, the radiologist or the interventional radiologist would be able to real-time modify the position of the needle to acquire the proper biopsy. So this would make it much shorter. Another very important application, which is very popular nowadays, is MRI-guided radiotherapy. So this is an image of the Elekta Unity, which is a 1.5 Tesla scanner integrated with a linear accelerator. So what this does is it allows you to visualize during the radiation treatment the position of the patient, so the position of the tumor, the position of sensitive organs, and adapt our treatment based on this. But clearly, if this is not real time in any way, then we will be unable to follow any respiratory motion, or will be unable to follow any peristaltic motion and things like that. So it's of paramount importance here that we are able to accelerate the acquisition and the reconstruction with a significant factor. And another possible application, which is one of my favorites, is in breast MRI, breast cancer screening. So in breast cancer screening, we often use a quite elaborate protocol. This is an ultra-fast protocol, and it involves different sequences like diffusion imaging, T1 pre-contrast, T1 post-contrast, fast T1s, slow T1s, and a T2 image. And in the end, we want to look at subtraction images like the one on the right, to be able to figure out where possible finding is. So one of the possibilities of using AI for MRI reconstruction here would be that during the acquisition, we could already reconstruct the image and try to detect if something is available or not, if there's some finding or not. And if so, we could decide on the spot whether we want to acquire an additional sequence or not. There's another important rationale for AI-based MRI reconstruction, which is not in the speed, but in the image quality. So this is a typical pipeline for medical image analysis. So medical image analysis, we try to build machine learning models that read medical images and try to perform some kind of diagnosis. So one typical example is like in breast MRI screening, we want to read mammograms automatically, or maybe for this example, we would try to quantify the ventricle volume and any changes. So how this typically works is, so we have the image acquisition, this is the case space, we reconstruct to an image, so this would be an image of a brain, we apply a model and get the diagnosis. But one of the disadvantages of such an approach is that in the reconstruction, there are all kinds of assumptions on what the image should look like and so on, and it often doesn't take any uncertainty into account. So this is a possible lossy step. So ideally, what we would want to have is that we want to go from case space to diagnosis. And the reason that AI reconstruction is useful in such this aspect is because these models, the models from the previous slide, are typically deep learning models. So if you're able to build a reconstruction model based on deep learning, we could just concatenate these two things and it's just one big model, which has image in and diagnosis out. So to briefly summarize this for you, so why would you want to do it? First of all, neural networks are super fast, so speed in reconstructing images with AI will already help you in speed. So this would help you in the real-time adaptive radiotherapy or in these image-guided treatments or biopsies. It lowers the scan time and the reconstruction can be very fast. So in MRI screening, it would be a possibility. If we are able to reconstruct fast, we're also able to make real-time decisions whether to acquire different sequences or not. And one very important thing is the fact that you are able to learn a data manifold. So what these AI models can do is they can learn the prior of what you want to reconstruct. So if we want to build a reconstruction model that reconstructs brain MRIs, we're able to build a model which has knowledge that it has to reconstruct brain images. So we need less data to be able to reconstruct it. So you could imagine, for instance, that if you know the image we're looking at is a bunch of circles, it's much easier to reconstruct this because we only need to know a few parameters like the center and the radius of the circle. So how do we accelerate MRI acquisition? So first of all, as a reminder, we start with the case-space data, and this is very easy. We take the inverse Fourier transform and we get a good image. So this image is also an example from the fast MRI data set, of which Facebook has published a paper a few weeks ago on where they claim that we can accelerate this by a factor of 4, so get good diagnostic quality images. So how to accelerate this? On the left is case space. So we acquired every possible measurement here. So one possibility is to acquire less data. So this is accelerated by, I believe, a factor of 8. And only in the gray areas the data has been acquired. And still, based on this amount of data, we do want to get the same image of the same quality. And this is a much harder task than the previous one. So this is not just a Fourier transform anymore. So if you look at this from a mathematical perspective, it's reconstruction is a so-called inverse problem. So this is the mathematical description of an inverse problem. And to understand the symbols here, X is the object or the body part we want to measure. A is the so-called the forward operator. So the forward operator relates the object we want to measure to what we actually will measure. In our case, this is for the MRI, this is an inverse Fourier transform. We end up with the measurements, which is a k-space. And of course, nature is never that easy. We always have some kind of noise in the measurements, which corrupt the data and make this problem harder to solve. So for MRI, this noise factor zeta is typically a Gaussian noise, so that's pretty easy to model. And so the goal here in MRI reconstruction is okay. So we have our inverse problem. So the goal is to actually find an operator B such that when we have the measurements and we apply B to it, we get the object. So we are able to we get the image back. So as I mentioned before, if you would have fully sampled k-space data, this would be very simple. This would be the Fourier transform. But since we don't have this problem becomes much harder. And so we will use, in this talk, the whole goal is to use AI or neural networks for this. And if we look into the literature, almost all the state-of-the-art models nowadays use some kind of AI in the reconstruction. So to visualize that, so we have the data Y on the right, which is the measurement, the subsampled measurement, and we want to find this operator B such that it maps to the image. And the difficulty here is that the data Y is subsampled, and mathematically this makes the inversion of the operator A, so operator B is a kind of inverse of operator A, a very difficult problem. So if we want to have we want to build reconstruction models with AI, there are several ways to do this, and there are three big routes to go, and I'll give you an example for each one of them. First of all, the most simplest thing you can imagine is you use a standard, so you have your subsample data, you use a standard reconstruction algorithm, and you try to use a deep learning model or AI model to fix the mistakes it makes. So this looks a bit like this. So we have our subsampled k-space, and we assume this is just all measurements. So we try to reconstruct it as if we have all k-space data. So we end up with something like this, which is called a zero-field solution. And then we apply an AI or deep learning model, and we try to map this noisy image to a good image. So this is the simplest method you can imagine. And there's also an example in the paper, the original Fast MRI paper by Facebook, where they do this with a so-called unit. So units are also often used in segmentation problems, but you can just use them as well to map one image to the other. So this way, we train with pairs of good images and these zero-field images, and improve the image quality in that way. But it has a clear disadvantage, and the clear disadvantage here is that this way we don't incorporate any knowledge of MRI physics we have. So all this does is map a blurry image to a sharper image. So we throw decades of research and understanding of MRI physics overboard if we do this. So that's perhaps not the best way to do it, but there is another way to do this. So we could just map directly from the measured data to the output. So the measured data is the k-space here, and the output is a reconstructed image. And this was actually a popular paper a few years ago, which was a letter in Nature, where they show how to do this, how to map case-based data directly to reconstructed images. This model is called the AutoMap, and it's as simple as I mentioned. You just have the complex sensor data or case-based data. They add a normal neural network. This is a multi-layer perceptron. After that, they have a convolutional neural network, and they map this to the image. And in their paper, they mention, of course, that you can do this with all kinds of data. You can do it with normal Cartesian MRI or multi-channel MRI, or you don't need to stop there. You can even use some kind of radio telescope data. Anyway, all this type of measurements, all these type of reconstruction problems can be done with such a model. But again, it does have another disadvantage. Okay, sure. Sorry. One step back. So basically, they map the case-based data directly to the image with the neural network. This has the same disadvantage of the previous model, where we used the UNet to post-process images and improve them. So we basically don't use any knowledge of the MRI physics in this model. The only place where we use it is where when we generated the ground truth image. Another very important disadvantage here is that since in this model we use a multi-layer perceptron, this really limits the input size to the same input size as the model was trained with. And as you know, the input size can vary depending on what type of resolution we want to reconstruct to. So these are both important disadvantages. And of course, my model or our models, we will consider are model-based. So they combine a kind of learning with model knowledge. So they combine an AI model with the actual MR physics which is available. So how does it work? To understand this, we need to look a bit at how the forward model of MRI reconstruction looks like. So on one hand, we have the fully sampled image. So this is the image we get when we have all case-based data. And the relationship between this image and the case space is the Fourier transform, or the fast Fourier transform in this case. And what we actually measure is a subsample based on a sampling mask. So the sampling mask is just a number of ones and zeros, and ones denote where we actually measure the case space, and zeros denote where we don't measure, we don't have the case space. So if you multiply these, you get a sparsely sampled case space. So where the original sampling mask was 1, we retain the case space information, and otherwise it drops out. So once we have this sparsely sampled case space data, so which is the thing we actually measure, you can apply the inverse Fourier transform, or the sum of squares method, to get the so-called zero-field reconstruction. So basically we have the zero-field reconstruction, and the goal is to get an image that looks like the fully sampled image. So another thing which is important to understand here is that in MRI, often we use additional coils to measure the image. So we don't take one measurement of the whole image, but we acquire several ones by different coils. And another thing, based on these coils, we have so-called the sensitivity maps, which give a kind of a weight of the contribution of a specific coil to the final resulting image. So when we have all these ingredients, this is actually the prior knowledge. This is again an inverse problem. So if you write down the inverse problem for MRI, you get something like this. So X is the image, so the fully sampled image X here. This image itself is weighted by one of the sampling masks. And this weighted image is Fourier transformed, so we get kind of case space. And this P is the sampling mask. So what we measure is actually the object itself weighted by the sensitivity map, and then again masked out by this case space data. So in the model we incorporate this prior knowledge. And to do this, we use the so-called recurrent inference machine, and this solves the inverse problem. And the inverse problem, y equals ax plus noise, can be solved with an innovation way using a maximum a posteriori estimator. So the first term here is so-called the the likelihood. So the likelihood that the data we measure, the measurement belongs to a certain image, and we have a prior which incorporates the information on what type of image we try to reconstruct. So the recurrent inference machine solves this problem dynamically, so over a number of iterations and a different number of time steps. And let's look at this a bit in more detail and get a better intuition on how we are doing this. So this is the rim unfolded. And this is one of the recurrent steps in here. So the inputs to one recurrent cell is an estimate of what the image would look like. So typically this is the zero filled image. We don't just have the zero filled image, we also have the measurements or the subsampled case space. And based on this amount of these two things, we can compute the likelihood that the image we propose belongs to this measured data. And to quantify this, we use the prior knowledge we have derived, so the forward model, to figure out how far off our reconstructed images to what it actually has to be, using our forward model. And since it's a recurrent model, we also have so-called the hidden states, which are needed because out of this recurrent cell, we get the image and we feed it back into the cell itself using information derived within the cell. So this hidden state propagates through the network and keep on improving the image iteratively. So we pass the previous image, which comes out of the rim, back into the rim and continue like this. And we get a better and better image in each step. So we can look at the function, the update function itself in a bit more detail. So this is the function which updates the previous iterate, so which improves the previous input image. And it's a rather simple neural network. A GRU is a gated recurrent unit. It's a type of recurrent neural network. And as an input, it has at each time step as an input, it has the previous guess and the case space, the actual case space measurements. So as I mentioned, based on these two, we can use our forward model or the physics knowledge to compute how far off it actually is on these actual measured data points. Additionally, our GRU cells have so-called hidden states, which are required to remember that we actually are at a certain step in the reconstruction. So we have two hidden states here. And the output of one of these cells is the next iterate, and we continue like this. It's a pretty complicated model, but we also have an open source software package where we have implemented it, so you can play around if you want to. And with this version, with separate versions of this model, so we adapted them a little bit. We won two challenges. So one was the faster MRI challenge in 2019, where we won the single track. And this year we won the Calgary Campinas multi-channel MRI reconstruction challenge, which was presented at Middle 2019. And so the goal in the faster MRI challenge was to reconstruct images with subsampling patterns like this. So this is a zero filled image on the left, bottom left. This is a compressed sensing algorithm, which is nowadays used to reconstruct accelerated data. And compared with that is our recurrent inference machine. So you can clearly see that much more of the details are retained here, and we get much higher quality images. So as I mentioned, we won this. We were Team Amsterdam. And if you currently look at the leaderboard, we still are at second place, and this is a year later. I'm pretty confident that if we train our model for longer, that we still end up at the first spot. So the second challenge we did with this model was at the Middle, which is the multi-channel MR reconstruction challenge, where the organizer have provided us with 167 of T1 weighted brain scans with 12 channel data or with 32 channel data. So this is very high quality data. It's, in my opinion, quite a bit better than the fast MRI data. For the fast MRI challenge, we do have way more data, but they have much thicker slices, and they have less slices in the axial direction. And the goal of this challenge was to reconstruct, well, images with 12 channel data, which was called the track 1, with 2 different acceleration factors. And a second track was to reconstruct out of distribution data. So this basically means that the data we had to reconstruct was of a different scanner or of a different type of acquisition than the one the model was trained with. So this is a typical problem for AI models, and that if you try to apply them to data it has never seen before, it's really unpredictable on how it will respond. So these are 2 tracks, and in the second track they had data with more channels, and again 5 to 10 acceleration factor. So the sampling patterns were slightly different. So they had these Poisson type sampling patterns. And one of the difficulties here as well was the fact that, so typically in MRI acquisition, you're able to measure the coil sensitivities before you acquire the image. So in this challenge, they did not provide us with a coil sensitivity map. So we had to find a way to actually kind of compute these. But one thing you should know is that these sensitivities are kind of a low frequency version of our original image. And in the challenge, we saw that the subsampling masks were fully sampled in the center. This is called the auto-calibration signal, and we can use this to compute an approximation of the sensitivity map. So how we do that is we take the fully sampled case space, we subsample our image or case space that way, and we try to reconstruct the image on this center. So we get a sensitivity. This is a kind of sensitivity map. Real measured ones and post-processed ones look a bit smoother than this, but this worked pretty well for us in the challenge. And so this was there are 2 examples on the challenge data. So you can compare the target to the left, which is the fully sampled data, with the 5 times accelerated data in the middle, and on the right, in the right panel, you can see the 10 times accelerated data. So at this resolution, it almost looks the same, but if you look a bit more in detail, especially in the cerebellum, you see that especially at acceleration factors of 10, we do lose quite some fine detail. In the excuse me, with the acceleration, and with acceleration 5, we do keep most of the details, so which is quite a surprising thing. So this is a bit more in detail. It's zoomed in. You can definitely see that with acceleration factor 10, the result is a bit smoother than it is in the acceleration factor 5 or in the target itself. Especially here, you don't see any detail, which we do have in the 5 times accelerated data. So these are some more metrics in case you want to check this out later. But so the message is that this is an extremely good model to do MRI reconstruction. It's completely AI based, and it does incorporate the case space and the physics of the model itself. And we won VRT resonance. We won both of the challenges. So TU MRI submitted a new solution after the challenge. So we dropped here in the visual information index a bit, but we still we remain in the first place in both of these tracks in the challenge. So of course I can mention all this, that REM is an excellent model to do MRI reconstruction, but it's also an extremely complicated model to build. So because of this, we made the project open source and publicly available. So we called it Direct. It's a deep image reconstruction toolkit, and it implements this recurrent inference machine and several of the variants. And you can just run, it's available on GitHub. We have now version 0.1.2, so it still has a bit of bugs. But please do let me know if you find any and you want to try the model. It's publicly available on GitHub, and it works pretty simple. You just need to define template on what type of model you want to use, what type of data set you want to use, if it needs to, what kind of batch size, and so on. Which you want to use to train this model. I can understand this is a lot of information, so I would like to conclude with that. And if you have any questions, please do not hesitate to ask. Thank you.
Thanks very much, Jonas. I'm just looking through any of the comments and see if anyone has any questions or they want any further clarifications. Can I just ask?
Yeah, please go ahead.
In terms of training data sets and stuff,
yeah.
like the challenge was done on MRI knees, is that correct?
There are two challenges. So the 2020 fSMRI challenge is done on MRI data of the brain. So in this data set, I have T1 data, T1 weighted, T2 weighted, and FLAIR T2. All of the data they provide is fully sampled, so they did acquire all data, so we can prospectively subsample this and build models. And the previous challenge was knee MRIs, which were protein densities, fat suppressed and non-fat suppressed.
And are these from a range of vendors? So you have
I think no, they're no, they're from different scanners. I think there are two Siemens scanners, 1.5 and 3 Tesla. The Skira and the other one. So no, we don't have all of that. But in the Calgary Campinas challenge, they have different scanners. These are GE scanners, so there is quite some variability available freely online. These data sets are huge. It's like 5 terabytes in total.
Amazing. And do you foresee a problem? You know, you've got a robust algorithm which seems to be working. Do you foresee any challenges when you try and scale it to essentially creating something which is vendor neutral?
I don't. Yeah, I can imagine that there will be some significant challenges, but on the other hand, I don't think it needs to be vendor neutral. Nowadays, the vendors provide you with the reconstruction algorithms. These algorithms are also not vendor neutral, and they're very tuned to their data, so they get the best images possible. If you want to build a vendor neutral solution, you will have to make some compromises somewhere in quality, and I don't think it's necessary if you want to build it for a specific scanner.
Can I also ask a question? Oh, sorry.
No, but of course, you do have variability as well, which you did not anticipate. So people bring in new coil designs and things like that in existing scanners. So it should be robust against that and not necessarily against the vendors.
Just one question from my side. I was curious, were there any pathologies in the images in these challenges?
Yeah, sure. This was clinically acquired data, so there should be quite some pathologies in there. So one thing which they noted in fSMRI 2019 was that for some pathologies, especially in the knee, they're very small. This can just disappear at higher acceleration factors, but this likely just means that an acceleration factor of 8 is just too much for knee imaging. Right now, the fSMRI 2020 challenge is running, where they will also score on the visibility of pathologies. So there are pathologies, and they will score on the detectabilities of these.
Oh, okay. Because this was something I was really curious about, because of course, normal images probably can be accelerated a lot, but the question is really or do you have any idea how can you estimate what acceleration factor still preserves all pathologies?
And it depends on all pathologies. It's not always important to be able to visualize all pathologies, obviously, but for knees where the pathologies can be very hard to see, like maybe like very small meniscal tears, things like this. There was a paper by Facebook a couple of weeks ago, maybe a month ago, where they show that using these type of models with an acceleration factor of 4, so 4 for knee MRIs, they were still able to achieve the same diagnostic performance as non-accelerated data. So it's quite significant.
All right.
I'll just post a link to that paper in the comments section.
Yeah,
I think it was
it's an
the
excellent paper.
AAR.
Yeah.
Yeah, excellent. If there are any questions at all from the audience, please feel free to post them in the chat or in the Q&A box. Yeah, I mean, Shah, do you have any further questions?
Nothing from my side. It was a very, very interesting talk, and just want to thank Jonas again and our sponsor Barco for allowing us to have this session.
Yeah, I agree. Thank you very much. It was really interesting, and yeah, let's see what we see of that in the future.
Thank you.
So yeah, I think with this, as Shah already said, I think we can close this session. It was really an interesting webinar, I think. Again, thanks to all viewers and listeners. Thanks to Shah for his excellent moderation. Thanks to Braco for sponsoring. And of course, thanks to you, Jonas, for presenting. And see you next time around. And of course, there's our upcoming annual meeting in October. So watch the newsletters, and we'll be announcing the modalities of the meeting soon, I think, and the abstract submission should be open. So whoever wants to present their works there, yeah, we're happy to receive your submissions. Thank you, everybody.